Welcome back, everybody. We are going to be working on our astronomic observations lecture. This one, we're just going to go introduce one, the lecture part, and then two, what we're going to be trying to attempt on Thursday, tomorrow, the 29th, for astronomical observation lab, excuse me, getting tongue tied, as well as doing a couple of solar observations and then moving on to GNSS comparison of that. So for today, or just for future notes here, let me clear this stuff out of the way. Let me actually pull up an actual calendar here for you guys. Um, so we are working on, what is this, week 9, right? Next month. So we're going to be having week 10 show up next week, and that's going to be the lab practicum. The lab practicum will be on Thursday, the 5th, right? So if there's anything else you guys need to clean up on for the rest of the labs or anything like that, you guys can finish that on the 3rd. And then Thursday will just be the lab practicum. Again, I will be handing that out on Canvas for you guys, and me and Evan will get together and discuss. He wants to emphasize on for you guys, but most likely we're going to do, again, total station setup, probably another level loop, and then maybe something else in between those two things, but most likely something to that effect. I will post something this weekend for you guys on campus, so that way you guys can have it and review it. And then we will meet the final. I will be posting that on this weekend as well. I will post that for you guys, and that will be due by Friday the 13th. All right, so that's our due date for that one, for the final. And again, that's all posted on Canvas for you guys, and you guys can take a look at it and start on the final. All right, so let's go started with astronomical observations. So a couple of key notes here. This is an old sheet that Professor Duryea gave me some time ago, but it had to change match because astronomical observation are kind of like a historical way of establishing bases of variance. So that's the whole reason for this lecture is how did they establish bases of variance with an old survey. So good example or a good, let's see, let's pull up our handy dandy county survey index here that the county has available for us. So, in olden times, pre-GPS, we can see if we can find something and some type of astronomical. Let's see. So, like E, so let's see. So that's exactly one of these ones like this. So if you look at this narrative, so this old survey back in March of 1988 says the basis of bearing of the survey is track 1080 Washington Park, a time method solar taken where shown on the map indicated that the bearings are 0 degrees 4 minutes 50 seconds true of north. 1872 meander. So that's again another time. So again, this is done by our surveyor Erwin Ritter. Did many around the basin, but again, he also took. So this was a perfect example of how to establish a basis of variance via time solar, and this method has been outdated as we will go through our book here, but that was one of the first ways of establishing a basis of variance for bound field. All right, so let's just work through this introduction. We'll look at the keynotes here that, and again, I can post this on Canvas for you guys, so that way you guys can have that as well. So a couple things here. So astronomical observation surveying consists of observing conditions of the sun and certain stars. The principal purpose, and this in plane surveying was to determine the direction of astronomical meridian in orbit. The resultant azimuth was needed to establish directions of new property lines so parcels could be adequately described, to retrace old property boundaries whose description included variants that were determined by astronomical methods, to specify directions of tangents on route surveys, to orientate map sheets, and for any other purposes. These procedures have been replaced with GNSS surveys, where coordinates of viewpoints are established on the ground, either using static or kinematic GNSS methods, as discussed in chapters 14 and 15. From these coordinates, either geodetic or grid azimuths can be determined for a line, right? So same thing here. Latitude and longitudes of points can also be determined by making astronomical observation. However, it's seldom, if ever, done today for two reasons. The field procedures and computations involved, especially for longitude, are quite difficult and time-consuming, especially for accurate results. Two, the use of global navigation satellite systems has made determination of flats and longs a rather routine operation. So again, GNSS is the most common use method nowadays. Thus, in this appendix, only astronomical methods for determining azimuth are discussed. For a more thorough presentation, that's a different book. You gotta go through this. So anyways, let's go to this figure here. All right, so let's expand the definition of astronomic meridian given in section 7.4, that was chapter 7. So at any point, it is a line tangent to and in plane of the great circle. So you have the great circle here passing through all the way across the Earth, all right, through the point, and the Earth's north and south geographic poles. This is illustrated in C.1 to this figure, where P and P. Forget, it's always on the tip of my tongue. Figure out now. I'm just gonna call it P secondary. So we have P and then P secondary are the poles located on the Earth's axis of rotation. So then you have arc of PA, P secondary is the great circle through A, and that line AN. So you have this right here, right? The astronomic meridian tangent to the great circle right here, right? Tangent to the great circle at A in the plane BOP secondary A. We have BO, so we have E and P secondary, we have PO, PA, right? And A. So again, with an astronomic meridian established, the astronomic azimuth of sorry, now I'm spacing Greek. But any lines such as AB, figure C1, can be readily obtained by determining horizontal angles of NAB. So we have N, A, and B. Figure out our angle here, right? The angle here. All right, our angle. So astronomical observations are not necessarily required on every project where azimuths and bearings are needed. If a pair of intervisible control monuments from previous surveys exist, and the azimuth for bearing is known for that line, new directions can be referenced to it also. So quick overview of usual procedures for determining the azimuth, right? So let's look at figure C.2. So we have, good morning, hang on, we'll clear this. All right, I'm back. Sorry, guys. So what happened there is I had a couple gentlemen from ODOT show up. They're they need to get up to the roof of our building for speaking of GNSS, so using one of we have a base point up there on our roof. So that's what they needed to come out here and do, update their antenna. Anyways, so quick overview of our figure here. So we have our, when we taking measurements here, we have our A, or where we're set up, our reference station, the azimuth, azimuth of the star, we have east-west, we have the horizon of the well, and then we have what we call the lower accumulation LC, we call our star, eastern elongation, have the western elongation, upper accumulation. So again, we're using our stars and the sun to determine that out. So let's go walk through this real quick. So the figure, imagine that P is the extension of the Earth's polar axis. Okay. And CS is a star, which appears to rotate about P due to Earth's rotation on its axis. Point N is the horizon, this is on the horizon vertically beneath P. Therefore, line AN represents true north. For the situation shown in the figure, the general field procedures employed by surveyors to define the direction of an astronomical system column sets a total station set up and leveled at one end of the line as to be determined line A. The station at the line's other end, like B, is carefully sighted at the instrument's four-long circle index 0 degrees 0 minutes 0 seconds. The telescope is turned clockwise, the star carefully sighted. The horizontal and sometimes vertical circles of this instrument are read at the instant of pointing on the star. But the precise timing of pointing is recorded and the horizontal angle is recorded when reference mark to the star, like the angle. Right, from to X. Office work involves obtaining the precise location of the star as silence, not premise. Reading stars asthma based on operation of this data and calculating the lines patterns by measures falls on stars such as angle equals 360 plus minus the data. So again, any visible celestial body for which ephemeris data are available can be employed by in procedures outlined. However, the sun and the northern hemisphere Polaris, the North Star, are almost always selected. The sun permits observations to be made in lighted conditions during normal daytime working hours. Polaris is preferred for high ordinary accuracy. In the southern hemisphere, a star in the Southern Cross is often used. Accuracies obtainable in the determining the astronomic azimuths depend on many variables, including the precision of the instrument used, the availability and experience of the observer, weather conditions, quality of the clock or chronometer used to measure the timing of sighting, celestial body sighted and its position when observed, and accuracy of ephemeris and other data available. In the northern hemisphere, Polaris observations provide the most accurate results, with several repetitions of measurements utilizing first order instruments accuracies within plus or minus 1 second if possible. Sun observations yield a lower body of accuracy, but values accuracy within about plus or minus 10 seconds or better can be obtained if careful repeated measurements are made. So here we have ephemeris, right? So as noted previously, ephemeris are almanacs containing data on the positions of the sun and various stars versus time. Nowadays, ephemeris data are almost conveniently obtained through the internet. We have Jerry Wall of Bureau of Land Management, for example, maintains an ephemeris on the sun and Polaris on his website. So table C.1, which applies to December 2000, was taken from his website. The data in this table is used in connection with some of the example problems later in the chapter. All right, so here we have the declination, the Greenwich hour, yeah, the time, and then we have a couple more declination and then other parts of it. And then here is all the data for the dates of December. All right. So again, a variety of ephemerises published annually are available to surveyors for astronomical work. One of the most useful surveyors is the Sophia Celestial Observation Handbook, which I have available. And again, I'll put this on canvas. See what it was. The ephemeris. Download real quick. So annual year. So back to what we talked about here. It not only contains tabulated data for the sun, Polaris, but also some other brighter stars in the heavens. This booklet also contains sustaining and supports the material plus work examples that demonstrate the use of tabulated data computational procedures. So back to the definitions. Okay. So definitions are going to be a pretty good understanding of how all this works. So we have the zenith, right? Zenith is located where the plumb line projected upward meets the celestial sphere. Okay. Which is Z. Nidar is the point on the celestial sphere vertically beneath the observer and exactly opposite of the zenith. See that north celestial pole is P, okay, where the Earth's rotational axis extended from the north geography pole intersects with the celestial sphere. And then we have the south celestial pole, the secondary, as I say, where the Earth's rotation extends from the south geography pole intersects with the celestial sphere. Great circle, again, going all the way around on the celestial sphere, whose plane passes through the center of the sphere. And we have the vertical circle, that's any great circle on the celestial sphere passing through the zenith and nidar. Represents the line of intersection of a vertical plane, okay? And then we have the celestial equator, that's the great circle on the celestial sphere whose plane is perpendicular to the axis of rotation of the Earth. It corresponds to the Earth's equator, enlarged in diameter. And then we have an hour circle, is the great circle on the celestial sphere that passes through the north and south celestial poles. Therefore, hour circles are perpendicular to the plane of the celestial equator. And we have the horizon, a great circle on the celestial sphere whose plane is perpendicular to any direction of the plumb line. Celestial meridian, interchangeably called this local meridian, is a unique hour circle containing the observer's zenith. It is both an hour circle and vertical circle. The intersection of celestial meridian plane on the horizontal is line H secondary O0, or sorry, OH figure. This figure. So we have this horizon, we have O here, right? All right, let's go see what else. Well, okay, so this one, the astronomical and PZS triangle, right, is a spherical triangle, vertical are the pole, P, zenith, Z, and astronomical body S. Because of the body moves through the diurnal circle, the angles in this triangle are constantly changing. Again, the azimuth of a heavenly body is the angle between the observer on the horizontal horizon plane, clockwise from either north or south to the vertical circle through the body. Right? From azimuth, the north is represented as arc of HS secondary, and it equals to the angle of the PZS triangle. So time, go for this part here. Yes, sidereal time, like sidereal day, is an interval of time between two successive upward accumulations of vernal equinox over the same meridian. Sidereal is a star time. Any location at any instance, it is equal to the local hour angle of vernal equinox. Apparent solar time. An apparent solar time is the interval of time between two successive lower accumulations of the sun. Apparent solar time is sun time, and the length of a day varies somewhat because of the rate of travel of the sun is not constant. Since the Earth revolves around the sun once a year, there is one less day of solar time in a year than sidereal time. Thus, the length of sidereal day is shorter than solar time by approximately 3 minutes and 56 seconds. All right. Mean solar or civil time. This time is relative to the fictional sun called the mean sun, which assumed to move in a uniform rate. It is base for time and the 24-hour day. Equation of time is the difference between apparent solar and mean solar. Its value changes continuously as the true or apparent sun gets ahead of and then falls behind the sun. And then we have standard time. This is the time of meridians 15 degrees or 1 hour apart, measured eastward and westward from Greenwich Eastern Standard Time at the 75th meridian, different from universal time or Greenwich Civil Time by 5 hours earlier, since the sun has not traveled from meridian in the United States. Standard time is adopted in the United States, making it blue because of some time locals previously used. Daylight savings and things are equal to standard time. This assumes that essentially daylight As previously noted, stunning star conditions that really depends on given the first time. Observation time on the other hand, important standard and daylight time. The location there or must be based on long review. So the frequency to based on different zones in the United States, one chooses standard meridians and then the power of the ability standard. Pacific, reads standard and then do that for. So let's go to time. Um, history. Let's go back to, let's get into the computation. So we'll get a calculator into the formula. So just a couple seconds, and then we'll have computations. So computation from azimuths from the Polaris observations. In this method, only horizontal circle readings for the time need to be recorded when the star is sighted. A vertical circle reading is for at least one pointing is recommended. However, to ensure that correct star has been sighted, to make the observations, the instrument set up leveled on one end of a line whose azimuth is to be determined. In the field procedure, the other line is to be first sighted, then horizontal angle between the star. To eliminate effects of the instrumental errors, equal number of direction and reverse observations are taken and the results averaged. The computations after fieldwork require the solution of angle Z in the astronomical PZS triangle. Two formulas for Z that are applied in the hour angle method derived from the laws of spherical trigonometry are Z equals tangent inverse times sine of t over cosine of the angle times tangent minus the sine of the angle times cosine. And then we also have Z equals the tangent inverse of negative sine local hour angle over cosine and tangent minus times tangent minus the sine times cosine of local hour angle. Upon the geometry upon the three equations are based shown more clearly in the figure C.5, right? Using the PCS triangle, the latitude of the observer's position is arc HP, thus PC is 90 minus latitude or cold latitude. Declination is the star of S secondary or times S. So SP is 90 minus declination or polar distance. Angle ZPS in the figure is T, the meridian angle, which relates to the local hour angle of the star. Diagrams such as those in figure 6.6 are helpful to understand the determining T angles and local hour angles. These diagrams show the celestial pole at the center of the Earth's diurnal circle as viewed from the observer's position within the sphere. On the diagrams, west to the left of the pole, east is to the right, and the apparent rotation of the stars is counterclockwise. The angle between the meridian and the Greenwich and local meridian through the observer's position is longitudinal of the station occupied. The star's Greenwich hour angle for the observation time is taken from the ephemeris sketching angle and Greenwich hour angle. Approximating to scale on diagrams such as those in figure C.6, meaning that makes the leader star's position. So as we're looking here, and from figures C.6, you can see that the local hour angle in the western hemisphere can be computed. So you can see here, we have our observer's time, right? We have what we have our 90 minus F, or yeah, so that would be our latitude. We have our angle here, which would be our polar distance, sorry, and this is polar latitude, right? We have our circle through here. We have our zenith. That's how we can determine our computations for Z. Figure here, we have P, right? We have Greenwich, we have our L, and then we have our angle between the two, and then we have the star, the local Greenwich. Same thing from this side. This is the westward movement. Computation of the meridian, sorry, angle T. Again, local Greenwich, and then there's T from L, G, and then we have our star and motion. So again, another table here, 6.C43. So going down to this table. So for the Eastern Hemisphere equation, we have local equals GHH plus angle. So in the figure of C.6a, LHA is between 0 and 180, where the star is west of north, as seen in 6.B. This guy here. It is between 180 and 360. If the star is east of north, also T, local hour angle. If the star is west of north, and then we have T equals 360 minus the local hour. If the star is east of north, the relationship between local hour angle of the star and the sine of Z is obtained by using equation C.5. So equation C.5 is your sine. You have the polar distance, right? The polar distance of the sun equals the polar distance of 0, or our base, right? Plus the delta between 24 and 0 time, universal time over 24 plus constant of this number. Then we have times your base time times the sine of 7, constant 7.5 times your universal time, right? Okay, so your polar distance is the tabulated declination of the sun and the day of the observation. And we have polar distance, it's the tabulation declination of the sun at 24 hours, universal time 1 on the day of the observation, right? And universal time is unit of the observation. So observers of the sun can be made directly by placing a dark class filter over the telescope, objective lens, total stationary should never be pointed directly to the sun without an objective solar lens filter. Failure to heat this warning may result in serious damage to the electronic components of the total station. Additionally, the observer should never look at the sun without the solar filter in place, or permanent eye damage will occur. Take that as a note when you guys do the lab. Second major difference depends on the method of the sun pointing on the sun, because the objective lens filter allows the observer to see the instrument's crosshairs in the sun's illuminating circle. The most precise pointing will occur at the trailing edge of the sun, as shown in figure C.6. Thus, the observer should place the trailing edge on the sun near the vertical crosshairs in figure 6.A. Then wait as the sun moves and record the time when trailing edge of the sun touches the vertical crosshairs, as shown in C.6.B. When using this field procedure, or any field procedure that involves edges, a correction must be made of the sun's angle for the sun's semi-diameter. The sun's semi-diameter varies with the distance from the Earth to the sun. The values are tabulated for each day in the ephemeris. The correction must be applied for the semi-diameter as computed. You have C, semi-diameter equals the sun's semi-diameter over the cosine of A little h. The correction for the sun's semi-diameter can be avoided by using rolled-off solar prism. The roll-off of solar prism is a device designed specifically for sighting the sun. It is easily mounted on the objective end of the telescope, and by means of prisms produces 4 overlapping images in the sun pattern, as shown in figure C.7. These were 6.7. They must have had those wrong. They must have those wrong here. These guys, hey, that must be figure 6.7, A and B. That's what they're specifying. But yeah, actually not. We're gonna go with tab later. Moving on. To compute the azimuth of a line from an observation of the sun, the hour angle equation, C.2 and C.3 can be deployed. All right, the same ones used for polar observations. Again, latitude and longitude can be taken from the USGS quadrant map and declination extracted from the ephemeris for the time observation. Right. So let's go on to the notes here. So again, quick notes here. Appendix of the astronomic observation. Number one, introduction, right? We have the astronomical consisted of the positions of a star, time and place, typically sun and Polaris, North Star. Any star can be observed if the ephemeris is available. It's an ancient practice, so it's outdated. All right. So purpose of the astronomic observations, determination of a line based on astronomy, which is BLM standard practice. When GPS surveying is not an option, again, remote location, visibility, latitude and longitude can be determined, but again, very hard calculations for longitude. Approach, understand basic astronomy, field observations and calculations. Spherical geometry. The universe is not a flat piece of paper. Basics of spherical geometry. The shortest distance between 2 points is an arc. The intersection of a plane and a sphere make a great circle. Right, shown here. Here, right? Basic astronomy. Astronomic north, the great circle that passes through the north and south geographic poles. The axis of rotation, and astronomic meridian. So basically, the astronomic meridian at any point A is tangent to an involved plane of the great circle passing through point A and the north and south geographic poles. Number two, astronomic azimuth 2 from A to the angle to point B or N from the angle from the astronomic meridian used in field surveys or the lab this Thursday, be next week, this Thursday. Obtained by observing a known star at known time and measuring any angle to control to another control point. Now we have celestial sphere. The Earth is center of the sphere. All stars are projected onto the base of the sphere. So based on that, we will have field procedures. We will have the lab for the azimuth by solar observation. Okay. Again, I will be putting this on Canvas. Have field notes. How we want to set that up, right? Okay. We have computations. We have our checks here. I will be providing the one calculations here. We'll be providing the ephemeris here. I'm going to get the 2024. I'll show you if I can find the 2024 almanac there. Write that. Oh, calculate at this solar time. This one. I'm going to write this down. Yeah. And example, right? All your information and your information of what days are, your ephemeris data, your field observation data, computed information, everything else. obviously see the computations. So with that being said, let us move on to the other portion of the lab, which is wherever you guys do this. Just pull this one, this. So whenever you guys do, you guys are gonna do a story date. So you guys are gonna calculate those. And then with the GNSS, because they're not gonna be the same, but you're also just gonna see what compared between GNSS and your astronaut, your control points and everything. So wherever you guys do that, wherever Evan has you guys set up for this whole project, and you guys do your astronomic readings, get your basis of bearing between two control points. You're also going to take measurements on those two control points with GNSS receivers and compute and write those down in your field books, compute, and then you're going to take the inverse of those and then figure out what your azimuth is between those 2 points and compare it with the astronaut. And that's what I want to see on field book. On the second page, you're going to have sonar observation. You can dig through that information. You got to figure that out, and then you can come up with your azimuth, and then as well as we're going to get coordinates using GNSS. Guys, email me with any questions. I've been kind of missing here and there. Just work has been pretty much all over the place. I don't have a set schedule on, I'm out of town here or there. I'm running around, deal with all kinds of different projects. So I'm trying to keep up, but right now it's pretty difficult. We're all kind of just itching at that, June 12th, 13th day to show up so we can run the class. But for now, I'm just going to try to get you guys as much information as possible with these courses, and try to upload some other things, and then as well as trying to upload the final for you guys, and that way you guys have all the information for you. Be ready to take to get this class done. All right, guys. Good talking to you guys again.